Consider an electric dipole consisting of charges plus Q and minus Q, separated by a small distance 2a, with its axis placed along the x-axis and the midpoint of the axis of the dipole at the origin. The charge plus Q lies on the positive x-axis at A, and the charge minus Q lies on the negative x-axis at B. The electric dipole moment P due to the dipole is equal to 2aq, and the dipole moment P points from minus Q towards plus Q. Let this be equation 1. Consider a point P in the electric field of the dipole in free space, at a distance r1 from the charge plus Q, and distance r2 from the charge minus Q. The net electric potential at point P due to the electric dipole is equal to the algebraic sum of the electric potentials due to the charges plus Q and minus Q of the dipole. And is equal to 1 by 4 pi epsilon naught into Q by R1. Similarly, the electric potential at point P due to the charge minus Q is V2 and is equal to minus 1 by 4 pi epsilon naught into Q by R2, since the charge itself is negative. According to the principle of superposition, the net electric potential at point P due to the electric dipole is denoted by V, which is equal to V1 plus V2. Substituting the earlier expressions for V1 and V2 in the equation for V and simplifying, we get the net electric potential V is equal to Q by 4 pi epsilon naught into 1 by R1 minus 1 by R2. Let this be equation 2. Theta is the angle made by line OP with the direction of the electric dipole moment. From the geometry of the figure, using the cosine rule for the triangle PAO, we have R1 square is equal to R square plus A square minus 2AR cos theta. This can be written as R1 square is equal to R square into 1 minus 2A cos theta by R plus A square by R square. Let this be equation 3. If R is much greater than A, then the ratio A to R is much less than 1, and hence the term A square by R square in equation 3 can be neglected as it becomes very negligible. Then we get R1 square is equal to R square into 1 minus 2A cos theta by R. This implies R1 is equal to R into 1 minus 2A cos theta by R power half. Therefore, 1 by R1 is equal to 1 by R into 1 minus 2A cos theta by R power minus half. Using binomial expansion of the terms in parentheses, we get 1 by R1 is equal to 1 by R into 1 plus A cos theta by R. Let this be equation 4. Similarly, using the cosine rule for triangle PBO, we have R2 square is equal to R square plus A square plus 2ar cos theta. This can be written as r2 square equal to r square into 1 plus 2a cos theta by r plus a square by r square. Let this be equation 5. If r is much greater than a, then the ratio a to r is much less than 1. And hence the term a square by r square in equation 5 can be neglected since it becomes negligible. Then we get r2 square is equal to r square into 1 plus 2a cos theta by r. This implies r2 is equal to r into 1 plus 2a cos theta by r power half. Thus, 1 by r2 will be equal to 1 by r into 1 plus 2a cos theta by r power minus half. Using binomial expansion of the terms in parentheses, we get 1 by r2 is equal to 1 by r into 1 minus a cos theta by r. Let this be equation 6. Substituting equations 4 and 6 in equation 2 and simplifying, we have v is equal to 1 by 4 pi epsilon naught into q by r into 2a cos theta by r, which will be equal to 1 by 4 pi epsilon naught 2a q cos theta by r square. We know that the dipole moment P is equal to 2aq, and hence net potential V is equal to 1 by 4 pi epsilon naught P cos theta by r square. Let this be equation 7. If r cap is the unit vector along the direction of OP, and since P dot r cap is equal to P cos theta, then we have net potential V is equal to 1 by 4 pi epsilon naught into P dot r cap by r square. The potential V as obtained by equation 7 is for the distance r, which is very large compared to A. If we consider point P on the positive x-axis, then the angle between the position vector of point P and the dipole moment of the dipole is 0. Then the potential at P due to the dipole V is equal to 1 by 4 pi epsilon naught into P by r square, as cos 0 degrees is equal to 1. If point P is on the negative x-axis, then the angle between the position vector of P and the dipole moment of the dipole is 180 degrees. The potential at P due to the dipole is V is equal to minus 1 by 4 pi epsilon naught into P by r square, as the cosine of 180 degrees is minus 1. For any point on the equatorial plane of the dipole, the net potential will be 0. Since plus q and minus q cause equal positive and negative potential respectively on the plane, and as theta is equal to 90 degrees. Therefore, cos 90 degrees is equal to 0. When the position vector r is rotated about the dipole moment vector P, keeping the angle theta fixed, then the points corresponding to P on the cone generated will have the same electric potential. We also observe that the electric potential V due to the dipole is inversely proportional to the square of the distance of the point of observation in the electric field of the dipole. In the case of a dipole, we have calculated the net potential due to a system of two charges. Now, let us consider the electric field due to a system of charges. Say, Q1, Q2, Q3, and so on up to Qn. Let us consider a point P in the electric field of the charge configuration. Let the distances of Q1, Q2, Q3, and so on up to Qn from point P be R1, R2, R3, and so on up to Rn respectively. The potentials due to Q1, Q2, Q3, and so on up to Qn at point P in the electric field are represented by V1, V2, V3, and so on up to Vn respectively. Since electric potential is a scalar quantity, the net electric potential V at point P will be equal to the algebraic sum of the potentials due to the individual charges. Thus, it is V is equal to V1 plus V2 plus V3 and so on up to Vn. Substituting the expressions for the potential at point P due to individual charges, we get V is equal to 1 by 4 pi epsilon naught into Q1 by R1 plus Q2 by R2 plus Q3 by R3 and so on up to Qn by Rn. Let this be equation 8. To obtain the potential due to a continuous charge distribution, we first divide it into a number of small volume elements of charge density ρ, such that the small volume elements have a volume dV each and a charge ρdV each. Then we find the potential due to each such volume element, say dV'. Then the potential V due to entire charge distribution is then obtained by integral dV', since this gives the sum of potentials over all such distributions. Now let us look at an example of uniform charge distribution. Let us consider a uniformly charged spherical shell of radius r, with a charge Q distributed over its surface. For any point P, which is at distance r greater than r, we have the potential due to the spherical shell at that point as V is equal to 1 by 4 pi epsilon naught Q by r. This equation holds good for all points that lie on the sphere or outside the sphere. Let this be equation 9. Since the electric field strength E for all points inside the spherical shell is 0, the electric potential has to be constant for all such points. The electric potential at any such point which is inside the surface will be equal to the potential on the surface and will be equal to 1 by 4 pi epsilon naught Q by r.